So, okay. Welcome to the last lecture of this mini course. And today we'll see what is the telescope conjecture. So please start.
All right, thank you. This lecture may be a little shorter than the others, but here we go. So I'm going to remind you of what happened in the previous three lectures. So I talked about some algebraic machinery behind complex cobordism theory in the first lecture, and this has a lot to do with formal group laws and their classification and endomorphism rings in characteristic P. Then in lecture 2, I talked about the chromatic resolution in its algebraic form, and that led to something called the chromatic spectral sequence and the chromatic filtration of the Adams-Novikov E2 term. And this was the subject of the paper, the joint paper by Haynes Miller, Steve Wilson, and myself. In lecture 3, I described how there's a geometric underpinning for this. There's a geometric form of the chromatic resolution that's defined using Bousfield localization with respect to certain the Johnson-Wilson homologies E of H that were introduced in lecture 3. Now, there's something that I left out of this account, and that is in the early 70s, there was a construction of what are called periodic families of elements in the stable homotopy groups of spheres, and they're known as Greek letter elements. Now, I haven't mentioned this so far, but I'm going to talk about it now because it was a very interesting example. It was the first time that we had anything systematic happening in the homotopy groups of spheres. Up until 1970, the homotopy groups of spheres appeared to be very chaotic. It was a lot of ad hoc calculations, and it was hard to see any patterns in it. So these periodic families were the first really interesting patterns. And it turns out we eventually learned that everything in the homotopy groups of spheres is part of such a pattern. But I'm going to start with the simplest examples. So in the first lecture, there was something that I called the Greek letter sequence. So this is a short exact sequence of comodules, BP star. Well, it's a short exact sequence of BP star modules that happen to be also comodules over BP lower star BP. So this involves quotients of BP star by certain ideals that are indicated here. Now remember that BP star itself is a polynomial algebra on V1, V2, V3, etc. And the dimension of V sub H is 2p to the H minus 2. So there were short exact sequences of this form. Now, these short exact sequences, each such short exact sequence leads to a long exact sequence of ext groups in which the connect will denote the connecting homomorphism by delta sub H. So delta sub H goes from an ext group for BP star mod IH to an ext group in 1 degree higher for BP star mod IH minus 1. Now, we know something about the ext0 groups for these gadgets. We know that ext0 for BP star itself is a copy of the p local integers in dimension 0. And we know that for positive H, the ext0 group for BP star mod IH is a polynomial algebra on V sub H. Polynomial algebra over Z mod P. Now, for each positive T, we can define an element alpha T that lives in this ext group. So it's obtained from this short exact, so you do this short exact sequence up here for H equals 1, which means that if H is 1, then these two guys are each copies of BP star itself, and this map here is multiplication by P, and we know that the X group for BP star mod P is Z mod P on V1. So we can look at the, we've got elements, V1 to the T lives in here, and its image under the connecting homomorphism lives in this group. And this represents, if the prime is odd, this represents an element of order P in this stable stem, this homotopy group of the sphere spectrum. For T equals 1, this dimension is 2P minus 3, and this is the first positive dimensional element in the P component of the stable homotopy groups of spheres. This is if P is odd. For P equals 2, it's a little different. Now, these alpha T's comprise what we now call a V1 periodic family. So, to repeat, this is the short exact sequence that we're interested in. X in X0 of this group are all the powers of V1, and we can look at the image of each positive power under the connecting homomorphism, and that gets us in X1 of this thing. Now, this algebraic construction has a geometric underpinning, a geometric antecedent. So let's say that, let's denote by V of 0 the cofiber of the degree P map of the sphere spectrum. So V of 0 is the mod P Moore spectrum. Adams showed that when P is odd, there is a map from the 2P minus 2 suspension of V0 to V0, a map that I'll call alpha. And this induces multiplication by V1 in BP star homology. And this means it induces an isomorphism in the first Morava K-theory, K1 star. So the way you get this homotopy element is you take this map alpha, you iterate it T times. So now that's a map from a big suspension of V0 to V0 itself. Then you precompose with the inclusion of the bottom cell into V0. And then you post-compose with the pinch map to, remember this guy right here, V0 is the mod P Moore spectrum. That means it's S0 with a 1 cell attached. And so there's a pinch map to S1. And then this composite then is, now this is in the stable world. This composite is a map from a sphere of this dimension to a sphere of this dimension. So it's an element in the appropriate homotopy group. And these elements constitute a V1 periodic family. Now, that's just the beginning. We can construct a V2 periodic family in the following way. Let's say that V1 is the cofiber of the Adams map that I talked about just now. So the Adams map was a map from the 2P minus 2 suspension of the mod 2 Moore spectrum into the mod 2 Moore spectrum, and it induces multiplication by little v1 in BP homology. So V1, big V of 1 denotes the cofiber of that map. So it's a CW spectrum with 4 cells in the dimensions indicated here. Now, independently, Hiroshi Toda and Larry Smith showed that if the prime is at least 5, then there is a map from a certain suspension of V1 to V1 that's indicated here. This map is called, I'm calling this map beta, and it induces multiplication by V2 in BP homology. Now, I'm hoping, I was hoping somebody was asking me what NPA stands for. So I'm going to tell you what NPA means.
What does NPA stand for?
It means no picture available. So I have a picture of Toda. I do not have a picture of Larry Smith. I couldn't find one. All right, so there's a map like this that induces multiplication by V2 in BP homology, and it induces an isomorphism in the second Morava K-theory. So that means all of its iterates are non-trivial. So we can iterate this map p times and get a diagram like this. So this is the map beta iterated t times. And again, we precompose with the inclusion of the bottom cell into this CW complex. And we post-compose with the pinch map onto the top cell of this CW complex. The top cell is in dimension 2p. So we get an element, when we compose them, we get a map from a sphere to a sphere, and this element is known as beta sub t. And these elements are known to be non-trivial for all positive t. So this works if the prime is at least 5. Now, at the primes 2 and 3, it's a little bit messier, but the details of that aren't important. Okay, so you might wonder, can we keep going like this? Can we do this? More. Now, algebraically, you can do a similar thing at all heights and at all primes. I mean, you have those short exact sequences, what I mentioned at the beginning. Let me go back here. So this is what I'm calling the Greek letter sequence. So you have these short exact sequences for all values of h and all primes p. So you can compose the connecting homomorphisms to get from x0 of this group to x upper h of BP star, and you can do the same kind of thing. You can do that on the algebraic world. Now I have to catch up with where I was. So algebraically, we can do the similar thing at all heights and all primes, and we can define this guy where here eta upper parentheses h stands for the h letter of the Greek alphabet. So it's alpha or beta or gamma or blah, blah, blah. So in the algebraic world of X groups, you can do this for all heights and all primes. But geometrically, we only know how to go one step further with this, and we can construct elements called gamma t for primes at 7 or more. But nobody knows how to go to the 4th step, and nobody knows how to construct a map like this that induces multiplication by v sub 4. People have tried, and nobody's able to do it. Now, I should mention that in each case where these maps can be constructed, it's done by what you might call brute force, in that you try to construct such a thing, and there are various possible obstruction groups that you have to deal with, and it turns out that all the obstruction groups vanish. So you get what you want by sort of dumb luck. All the groups where there might be an obstruction to doing what you want to do happen to be 0. All the homotopy groups that you have to deal with happen to be 0. But when you're trying to construct a map like this, that doesn't happen. There's a non-trivial obstruction group at every prime, and nobody knows how to calculate what the obstruction in that non-trivial group actually is. So nobody knows how to construct this kind of map. So we're kind of stuck there. But there is a way around this. So we can't get exactly what we might want in the height 4 case, but there is something something we can do, which I'm going to talk about now. So let's say we have a p-local spectrum, p-local finite spectrum X. Now, it's not hard to show that if kh star of X is 0, that means that kh minus 1 star of X is 0. In other words, if one Morava K-theory vanishes, all the lower Morava K-theory theories vanish. And we also know that kh star of X is non-trivial for large h unless X is contractible. Those are two things that are not difficult to show. So we're going to say that X has type H if H is the smallest integer for which the Morava K-theory is non-zero. And so, for example, the gadgets VH minus 1 that Toda constructed, that's V0, V1, V2, and V3. In each case, the type of VH minus 1 is VH minus 1 has type H. Now, the following was conjectured by me and proven by Devenotz, Hopkins, and Smith in their 1988 paper, Nilpotence 1. And it is this. The Bousfield equivalence class of a p-local finite spectrum is determined by its type as I've just defined it. Any two p-local finite spectra of the same type are Bousfield equivalent. And so in particular, a finite spectrum has type 0 if its rational homology is non-trivial. And in that case, any such finite spectrum is Bousfield equivalent to the p-local sphere. So that's far from obvious at the beginning, but it's a theorem that they proved. Now, a few years later, Hopkins and Smith proved the following. Let's say that this is the periodicity theorem. Let's say X is a p-local finite spectrum of type H. Then there is a map from a suitable suspension of X to itself, a positive suspension, that has the following property. It induces an isomorphism in the KH, the Morava K-theory indexed by H. And in every other Morava K-theory, it induces a map that's nilpotent. Some iterative of it is 0. So there is a map like this that induces an isomorphism in the first non-trivial Morava K-theory that's available. And we'll call this thing a V sub H self-map. Now, I didn't say that this map is unique, but it is asymptotically unique in the following sense. Let's say we have another map, V prime, for a different suspension, D prime of X. Then there are integers E and E prime with E times D equals E prime times D primes, and the ith power of V is the E prime power of V prime. So one power of one map is equal to another power of another map. So if you iterate these maps the right number of times, they become equal. Now, it follows from this that the cofiber of this map V has type H plus 1. This means that we can produce finite spectra of all higher types by iterating this process. And the class invariance theorem implies that the Bousfield class of the telescope associated with this map is independent of the choices of both X and V. In other words, you could start with any p-local finite spectrum of type H. Any one will do. And you could pick any self-map provided by the theorem, and the Bousfield class of the telescope that you get will be the same. And we'll denote this Bousfield class by bracket T of H. Now, let me emphasize, there is no T of H does not stand for a well-defined spectrum, but it does but there is a well-defined Bousfield class, because as I said, if you can start with any p-local finite spectrum of type H, there's a self-map provided by the Hopkins-Smith periodicity theorem, and you can iterate it and get a telescope, and the Bousfield class of that telescope depends only on the prime and the height H. Okay, now, so here it is again. Let X be a p-local finite spectrum of type H, then there's a map V which has these properties, and we call it a BH self-map. Now, the map from X to the telescope is necessarily a KH star equivalence. That means that there's a map from the telescope to the KH localization of X, and that is the same as the E of H localization. And that equality holds because the lower Morava K-theories vanish on X. Okay, so there's a map from the telescope of X to the LH localization of X, which we have which is computationally accessible. And that leads us to the conjecture, which is that the telescope conjecture, as I stated it in the 84 paper, is that this map is an equivalence. That's what the telescope conjecture says. This is trivially true for the case H equals 0. It's easy to check that, well, in the case H equals 0, the map you want is just multiplication by P. So you're inverting P, and that's the same as localizing with respect to K0, or rational cohomology. It's trivially true for H equals 0. Now for H equals 1, it's a non-trivial statement, but it was proved around 1980 by Mahold at the prime 2 and Miller at odd primes. So it was known to be true for H equals 0 and 1. When I made the conjecture, it was known to be true for H equals 0 and 1. However, in 1989, I began to think it was false for larger values of H, for H equal to 2 or more. So I made the conjecture actually in the late 70s. It appears in print in 1984, but by 1989, I was convinced that it wasn't true. It was actually false for H greater than or equal to 2. And this is now a theorem of Burklund, Hahn, Levy, and Schlank. So there's a picture of the four of them with me. This is when they announced their theorem at Oxford in June. Now, as I said, this is going to be a short lecture. The thing that's interesting about this conjecture is it's equating a geometrically interesting object, namely the telescope V inverse of X, with a more computationally accessible spectrum LKH of X. Now, what I mean when I say it's computationally accessible, let's look at the case where the height 2 case, then in the height 2 case, Toda's complex V of 1 is sort of the simplest example of a type 2 finite complex for a prime that's at least 5. And we know how to calculate the homotopy groups of LK2 of V1. And we know that it consists of exactly 12 V2 periodic families. We can say exactly what they are. Now, we don't know how to calculate the homotopy groups of the telescope. And it's likely that those homotopy groups are likely to have much more than 12 periodic families. In fact, they're likely, my guess is that there's infinitely many periodic families in this thing. So there may be infinitely many periodic families that are not detected by the localized atom spectral sequence. You can formally invert V2 in the Adams-Novikov spectral sequence for this gadget. And so you get something called the localized atom spectral sequence. It is known to converge to the homotopy of the Bousfield localization, but it's not known to converge to the homotopy of the telescope. And indeed, it doesn't. That's what that's what the four-author theorem says. The BHLS theorem says it does not converge to the homotopy of the telescope. Meanwhile, there is also the ordinary atom spectral sequence does converge to the homotopy of that four-cell complex V of 1, but it only sees 12 V2 periodic families. So you might ask, where are all the others? If the Novikov spectral sequence only sees 12 of them, but there are a lot more, how can that be? So this is what happens. You could have a V2 periodic family, but it's spread out over infinitely many Adams-Novikov filtrations. So in other words, you've got some, you could have some element in the homotopy of V of 1, and you could see it in the atom spectral sequence, in the Novikov spectral sequence, and then you could multiply it by various powers of V2, and eventually it's going to jump up to a higher filtration. Excuse me. It's going to jump up to a higher filtration, and then you're going to multiply a few more. You can multiply it by a few more powers of V2, and then it's going to jump again. And they're going to have to be infinitely many of these jumps. And that's the end of my talk. So thank you very much.
Okay, let's first thank Doug for the great talk.